Hi, my name is Stephen Marrone, and I'm going to talk to you about my senior project, Smart Safeguard. So for those of you who don't know, my senior project is a car crash detector and emergency first responder notification system. So what that means is, basically how this project works is you're going to plug it into your car, pair your phone with it via Bluetooth, and then just go and drive. And if it detects a car crash, if you're in a car crash, it will flash a light and buzz a buzzer for 15 seconds. And there's a button you can push that will tell it was a false alarm or the crash was really minor, like fender bender, so you don't want to text 911. So assuming it's a bad crash and it goes through and all 15 seconds go by without you pushing the button, then it will use your phone to text GPS coordinates of your latitude and longitude to 911 and letting them know that the crash has occurred. So it texts 911 for you when you can't contact them. So how this works is, basically I've been using the Arduino Uno. So this is the chip, the ATmega 328, which is the brains behind the Uno. And this is my PCB, by the way, so this is just a schematic editor in Eagle. But most of the work that I've done since the last presentation on my senior project has been in making a PCB. So this, again, is the ATmega 328, the main microcontroller, just a small 16 megahertz microcontroller. Here's going to be the GPS module. Here's the accelerometer. I'm using an analog device's accelerometer. A Bluetooth module over here. This is a voltage regulator that takes the 12 volts from the car jack and brings it back, or brings it down to 5, so that my Bluetooth module, microcontroller, and GPS can utilize it. One interesting thing about the accelerometer that I chose is it actually maxes out on 3.5 volts for the power supply. So in order to get around that, I would either need to use a whole new voltage regulator that goes from 5 volts down to 3.3 or something like that. But luckily for me, the GPS module has a built-in 3.3 volt voltage regulator on it. So I just tied that pin out to the accelerometer, and that was that. So again, there's a couple interesting things is I have breakouts for FTDI, which is basically allows me to program the microcontroller with with an FTDI breakout board, so I can program it when it's in the PCB. I have a jumper for the button, and then I also have a jumper for the reset pin on the Arduino. And the Arduino also controls some little things like the red LED, which blinks when the crash is detected, and we have a green LED, which turns on when the system is ready to go. And what happens, or how the system knows it's ready to go, is basically 5 seconds have gone by, so it can characterize the resting point for the accelerometer. The GPS has found a lock on satellites, and you connected your phone to Bluetooth. Now, normally all those, the GPS is the longest one by far. If you're indoors, which you don't really use a car indoors, so it wouldn't happen too much. But if you're indoors, it could take like at most a minute. But usually it's around 30 seconds. And if you're outside driving your car, it's probably even faster. But most of my testing has been indoors. I also did a layout for my PCB, and I'm going to show you that next. So this is my layout for my PCB, and since I've already done a lot of the explanation for the schematic editor, I'm not going to go too much in depth into this because most of what happened here was just like completing a puzzle. Just put all the components on and connect them until nothing overlaps and whatnot. But basically, how I made my PCB was I used IEEE's their mill PCB milling machine. So it can do at most 2 layers, so like 2 sides of a copper board basically. And it can't do vias though, so in order to just kind of keep it simple, I just decided to do a 1 layer, which did make it a little more difficult on some aspects of it because you can't use any vias or the other layer. So I need to actually go through some components which is really like underneath them. So for instance, this 5 volt line right here goes underneath the buzzer to connect to the jumper here for the button and the active high reset switch for the microcontroller. And also this Bluetooth serial data line goes under the LEDs, or sorry, the resistors for the current limiting of the LEDs. But other than that, there wasn't too much like anything crazy that went on here. But yeah, as I mentioned before, we have the 18 mega 328p in the center. We have the clock and two small capacitors for that. We have the buzzer here. We have the voltage regulator, some resistors that are just like pull up and pull down resistors. And then we've also got the accelerometer here, the Bluetooth module here, and the GPS module here. Yeah, and then these are all the capacitors. So the accelerometer has four capacitors total with it, 347 nanofarad capacitors, which set the bandwidth for the individual portions of it. So it's like the how fast it will update that pin, basically the voltage on that pin. And then here's the power supply filtering capacitor. And one thing that the first mistake I made while doing this was I did everything on the top layer, and Eagle defaults through-hole components, which I'm using all through-hole components, to the top layer of the PCB. And since all of my traces were on the top layer too, basically they connect the traces were on the same side as the components, so the traces were all mirrored since they're supposed to be on the bottom layer or the opposite layer of where your components sit. So that gave me a mirrored board, and some of my components couldn't be placed correctly. So that was a waste, but luckily it was pretty cheap to make a board, and then, you just give them the file and you can come back in like 10-15 minutes and it's ready. So it wasn't a lot of time to just make the correction and remake it. That was really the main problem I ran into while doing these. Other than that, the actual layout process was pretty easy. This is the Smart Safeguard PCB shown here with all of the components on it. So right here we have the GPS module, the buzzer, the voltage regulator, 16 megahertz crystal, 18 mega 328p, a Bluetooth module, we have the green and red LED, and we have the accelerometer. And then we're using the Arduino for power, so I'm just using 5 volts in ground to power this thing. The actual thing will be powered via a carport, which 12 volts would plug in right there for testing. Then I have my phone, which is connected to Arduino SMS, as we can see, and by that green light there. Then I'm going to shake this to simulate a crash. There we go. I'm going to watch my phone, so after 15 seconds, I'll get a text. There it is. And there we can see. Now if you plug these in to your Google Maps, you'll find my house, which is a little creepy, but don't do that. And then I'm going to show you what the back side of my PCB looks like now. So unplug it. And then on the back we have the PCB, which is exactly what you saw in Eagle, just printed. Thank you very much.